Okay, so hi everyone, welcome to our 8th virtual meetup on autonomous driving. It is probably going to be the last one because after these years of COVID, we are now really heading for physical meetings again, meetups again. And that being said, I'm super glad to have some really great speakers with us for this probably final virtual event. We have Aleksa Gordic from the AI Epiphany YouTube channel. I don't know if any one of you has already watched it. If not, then it's a strong recommendation. I watched the channel frequently over the past couple of months, and it's fantastic if you want to stay on top of recent developments in machine learning, and you really want to go all the way down to the papers and get explanations from Aleksa, including also the code that goes along with many of these papers. So that's super cool. And then we also have Matthieu Worm. He was nice enough to join us on very short notice yesterday when unfortunately it turned out that 𝐤𝐴𝐞𝐳 couldn't make it in the end. Matthieu is with Siemens. He is an expert for simulation and digital twins, and he'll do the second session today. With that being said, I'll hand over to Aleksa. Aleksa, go ahead. Looking forward to your presentation.
Awesome, thanks a lot. Let me just share the presentation. Okay, do you guys see it?
Yep, all good.
Awesome, cool. So yeah, thanks Felix for the introduction. Thanks for the invite. Basically, let me just preface this before even starting. I'll be presenting my personal opinion here and not that of my employer. And having said that, so this presentation is going to be about recent advances in deep learning, as you can see by the title. And yeah, let's start. And let me open up this whole presentation with a simple question, and that's: is stacking more layers all we need? And basically, I'm going to show you in this presentation, hopefully, that okay, that's definitely an important part of this of the trend we've been seeing. But aside from that, I'm going to show you some theoretical advancements that we've been seeing over the last years. And so it's not just stacking layers, and also we shouldn't be treating stacking layers as a simple thing. There is a lot of engineering going on, and yeah, so that's a common thread. So I'm going to briefly walk you through some of the most influential deep learning papers that happened over the last, I guess, 1 year or maybe a couple of years. And I'm going to start with convolutional neural networks because I assume that's something that's super relevant for this community. So yeah, basically the first paper is this ResNet strike stack, an improved training procedure in PIM. And you can see, like, I've linked all of the archives here. So maybe Felix can share my presentation like with people somewhere in the, I'm not sure how this platform works, but feel free to share the PPT so people can later just kind of skim through the slides and yeah, see the papers. By the way, I can't see anything. If you don't mind, like, feel free to just kind of turn on the cameras. That would be super cool, especially because of the recording as well. And yeah, awesome, cool. So let me tell you what this paper is about. So they basically show that we're failing to discriminate between advances in architecture design versus training procedures. And what I mean by that is they've taken a ResNet 50, which is a famous baseline. Like it's been there like since 2015. When it was introduced by Microsoft Research. And here we can see that depending, so on the left side, you can see you see my cursor, by the way?
Yeah.
Awesome. So here you can see models such as ResNet and DateS, which is the vision transformer, which were introduced, I guess, late 2020. And I've covered that in a video, like literally a couple of weeks after it was published. You can check out that one later. But basically, what I want to say here is A2 and T2 are some arbitrary training procedures. And you can see that depending on which training procedure you pick, you may end up with a different conclusion. So basically, with A2, it seems that a ResNet 50 is better than Vision Transformer. And if you take T2 procedure, then all of a sudden the AT is better. So all of this suggests that it's very important to jointly optimize both the training procedure for a particular architecture of your choice. And what these guys showed is that if you take, so as I said, the simple ResNet 50 baseline, and you apply these novel training strategies we've developed over the years, such as mix-up, cut mix, label smoothing, stochastic depth, FLAM optimizer, and others. Like, and yeah, if you don't know all of these in detail, it's not that important. I'm just gonna basically show you visually how some of these look like. So Meetup is an interesting one. So let me zoom in here. So what Meetup does is, instead of predicting, so if you have an image of a cat, instead of predicting a label for cat, you mix those two, hence Meetup, you mix them in the image space. So basically a simple linear interpolation of the images in the image space. And then as the target, instead of having 1 for the class, you kind of have 0.5 for all of the classes that were mixed up. And in general, you will not have just 2 classes. You can imagine having like 1,000 classes. All of these will be 0, except for these 2 classes that you've mixed up in your. It's a super intuitive, simple thing to do. And using methods such as this one, they managed to boost up the performance from 76%, which was the original accuracy, to 80.4, which is a huge boost. So yeah, this was very important because people started to think that, people reporting these older results, and they were underestimating how good these CNNs actually are. And so it's very important to do its justice, and this paper definitely did. So nicely continuing to this paper is this 𝐸𝐞𝐜𝐴𝑐𝑡 paper, a 𝐸𝐸𝐞𝐜𝐼𝑛𝑒𝑡 for the 2020s, where what they've done is they've again taken CNNs and they've applied various techniques, which I'm going to briefly tell you about. And after they've done that, they showed that 𝐸𝐸𝐼𝑛𝑒𝑡s, so basically CNNs basically can outperform vision transformers. So both the original 𝐕𝐢𝐼𝐴𝑡 from 2020, and here you can see swing transformer, which was a later advancement. So the thing with 𝐕𝐢𝐼𝑡s is a quick reminder here. The original one was very good for image classification and kind of outperformed CNNs on that task. But then they were not that good for dense prediction tasks, such as semantic segmentation, instance segmentation, object detection, etc. And then this swing transformer added arguably some CNN priors into it and achieved even better results on those dense prediction tasks. And then what 𝐸𝐸𝐼𝑛𝑒𝑡s authors have done is they've taken all of the advancements that have happened over the years that were kind of developed for vision transformers in particular, and they've taken some of those advancements and integrated them into the CNN. So here you can see in this table, starting from like on the top, you can see 78.8, this horizontal bar, which represents the baseline ResNet 50 plus some additional knowledge that the last paper on the previous slide introduced. And then starting from that point, they started adding various different modifications. So there is a bunch of them. I'm going to focus on maybe one of these. So you may recall, like since I think 𝐕𝐢𝐻𝐺 was published, we figured out that 3x3 kernels are something that empirically gives us the best results, is the best trade-off for CNNs, and we started using 3x3 kernels. And here, they actually, after introducing some of the changes, they showed that by having 7x7 kernel instead, that gives them the top performance. If they go above like 9, 11, then they the performance starts suffering. So 7 seems to be a sweet spot for this particular model. And yeah, with all of these, it's very contextual, obviously. If we were to change any of these other ones, probably 7x7 would not be optimal. But yeah, all in all, you can see that after you apply all of these, you get 82% like accuracy, top 1 accuracy on ImageNet, which is higher than the swing transformer. So that was cool. So those were some learnings how we can use CNNs and make them still competitive with other models such as vision transformers. Okay. So yeah, maybe we can open up for a short round of questions, and then I can continue, because yeah, I think makes a lot of sense to make this a bit more interactive. If there are some questions so far.
Sure. So there's a Q&A section. People can type in there or put it in the chat. Not everybody will be able to join via camera or microphone. But again, if somebody can quickly already type something in, that's great. Otherwise, Gaurav, anything that you already wanted to ask?
No, and I don't see any in the chat right now. So if you want to ask your question, I mean, just raise your hands and I can probably unmute you. So, but go ahead and put your questions in the chat, and Aleksa, you can go ahead.
Yeah, no worries. I'll just continue, but like feel free to interrupt me. Like the whole point of having a live person in front of you is to be interactive. Otherwise, I could just pre-record a video and it would be probably much better than this.
Wait, there's the first question.
Yeah.
Let's read it out. Being new to deep learning, how do we know what papers to follow or even where to look for papers? Which guidance do we have?
That's a simple question. Just follow my YouTube channel. I'm joking. I mean, there is a bunch of good resources. I think one of the main dangers for a new starter is to get into decision-making paralysis. Like you have too many resources out there. You have too many influencers, but not like who are sharing a bunch of different resources. I think just find one plan, like sit down and create a couple of days, like develop your own plan. Probably Coursera courses are a good start, and just execute. Like don't overthink too much. You're never going to make an optimal plan. Like just start learning from, let's say, Coursera or Fast AI courses, and then you can continue on from there. I basically have a whole blog dedicated to this topic, so we can post hoc share the blog or something like that. Cool. Okay, let me continue, and we can address every now and then a couple of questions. So, next topic are transformers, because as I mentioned, vision transformers is something that can help us even in the field of computer vision, since the vision transformers were advised. And so, scaling transformers has been a very important trend that we've seen since at least 2020 with GPT-3 that was published, I think, in like May 2020 by OpenAI. And recently, Deepmind published Gopher, which has, so GPT-3, just for like a recap, has 175 billion parameters. Gopher was recently published, and it has 280 billion parameters. And you can see the results here. You can see the Gopher, so the blue bars on this chart, which you can hopefully see on the screen. Basically, it outperforms GPT-3 across all of these different tasks. So yeah, medicine, maths, etc. And so after that, like very recently, we had, I think a couple of days ago, Google published this Poem paper that has 540 billion parameters, and it outperformed, I think it outperformed Gopher across various different tasks. So it's going even bigger. And then an interesting advancement that happened also a couple of days ago. It seems a lot of these papers were published in the last month or something. So Chinchilla was published, and they showed an interesting thing, and that's that we're probably not on the optimal point when it comes to making a trade-off between the size of the model and the data you feed it. And so what I've found is that actually for a given compute budget, it's a much better idea to lower the model size, so go from 280 to 70, so that's 4x smaller, and to instead increase data by 4x. And that way you roughly have the same compute budget, but like Chinchilla outperforms Gopher, GPT-3. I'm not sure how it compares with Poem, but yeah, you get the point. There is still a lot of things we don't know, like a lot of empirical things going on, and yeah, this is very exciting, and all of these can feed back into previous slides. Like all this research can help us improve other models. Okay, so having said that, Perceiver is another very interesting model that deserves a mention. So general perception with iterative attention, also from Deepmind. And the thing why this is interesting is because, as you may know, we usually have for all of specific domains, such as, I don't know, computer vision, for NLP, et cetera, GraphML, you always have specialized architectures. So depending on your modality, like whether it's video, audio, image, point cloud, text, whatnot, you always have specialized architecture, specialized training procedures, specialized data augmentation strategies. Everything is super curated for a particular domain. So what Perceiver instead tried to do is make the model that's modality agnostic, basically. So that means here, if you can see these green arrays, you can basically plug in an arbitrary modality, as I said, video, point cloud, whatnot. And basically that's and then you add the only thing where they have modality specific information is they add modality specific positional encodings plus some data augmentations, but that's everything. And then you have this generic generic perception architecture. So the cool thing and why this is very interesting is because it's computationally efficient, and that's I guess a trend that's super related to the scaling thing I was talking about, and we're going to see on the next slide a bit more about that. But like you can see here that I'm going to read this snippet from the paper. This results in an architecture with complexity big O, m times n plus L times n squared, and this is the key. By decoupling the input size and the depth, we can add additional transformer layers at a cost that's independent of the input size. So M is basically your dimensionality of your input modality, which can be very big. Like if you have an image that's like 1,000 by 1,000, that would be already, if we assume it's a grayscale image, whatnot, then that's already a million dimensions for your M. And so you definitely don't want to have your usual quadratic complexity that transformers suffer from, and that would be M squared. Instead, what they do is they have this cross-attention module that basically maps this onto this latent representation, which is much lower dimension, and that's denoted by N, this big N. And that's why we have M times N. That's the cross-attention, then plus L times N squared. Well, L is the number of these hidden transformer layers. And we only have N squared, where N is much lower dimension and independent of the input dimension. So that's super interesting thing that Perceiver introduced. And yeah, they say here that while we reduce the amount of modality-specific prior knowledge in the model, we still employ modality-specific augmentation and position encoding, as I already mentioned. Okay, so that's kind of a big deal. But all of this, what I've so far talked about, ties nicely into this blog post by Rich Sutton back in 2019 called Bitter Lessons. And if you haven't seen this one so far, I strongly recommend you go ahead and read it. It's literally a 5-minute read. And I'm going to here show you a couple of snippets of text from that blog. So Rich says here, the biggest lesson that can be read from 70 years of AI research, let me just move the WebEx thing here, okay, is that general methods that leverage computation are ultimately the most effective and by a large margin. The ultimate reason for this is Moore's law, or rather its generalization of continued exponentially falling cost per unit of computation. And then he goes on saying search and learning are the two most important classes of techniques for utilizing massive amounts of computation in AI research. And we've seen this trend with pretty much any domain you care about. Like, I don't know, like let's start with the classic AI problem, that's chess. We've seen like people back in the days, like in I think even 80s, 90s, you had like a bunch of PhD guys and girls who were like developing this for like 20 years and trying to develop various heuristics, and then all of a sudden you make this brute force algorithm called like Deep Blue, which is like based on search, and then you beat all of those methods. And then later on with Go, you had a similar story happening, and then Deepmind came with AlphaGo, AlphaZero, all of those 𝐵0 family of models, and they showed that basically leveraging computation, search and learning is what ultimately prevailed. So yeah, this is a very important thing to keep in mind, and why it makes sense. Like we shouldn't like take this for granted, but like if you just think about it, if you have a model that piggybacks off of computation, if you're leveraging computation, then you're basically connecting yourself to this exponential growth. And there are people who say that Moore's law is dead, and I studied electronics, and I would say I don't agree with that. And if you listen to some of the podcasts, like maybe Jim Keller, you have a nice podcast with Jim Keller with Lex Friedman, you can see that there is many other dimensions we can still leverage to make sure that this growth continues. And not only using classical computers, there is a lot of interest currently going on into neuromorphic computing, into sparse computations. Maybe Graphcore is a good company that does sparse types of computations, and Cerebras. There's a lot of startups and companies working on this like on clock. And so I think it's a smart idea to just extrapolate and still continue extrapolating the trends we've seen over the last decades with exponentially increasing computation being available. Okay, enough jabbering. Here is a very bad meme, and I'm going to stop here for a couple of maybe minutes and allow you to ask any questions if you have it.
So there's a bunch of questions now. I'll just get started. The first one is by Bob Crutch. A lot of improvements come from data augmentation. This was still about the earlier part of your presentation, data augmentation. But in the praxis, we are not having issues with lack of data. We are on the other side, too much data and many issues with insufficient neural network capacity. I guess it's more a comment than a question, but maybe you can comment back. Would you agree?
I mean, we haven't seen any decrease in the amount of data we have, in the amount of computation, in the amount of we have bigger and bigger models going on. So I wouldn't say that we're bottlenecking when it comes to model size. Like we've seen dense transformers that have over 500 billion parameters. PaLM is an example, like the Pathways language model from Google is an example. Then we had sparse transformers that are over 1 trillion parameters. Although, as you may know, when you do an inference using those, you don't activate all of the parameters in the model. But I don't think this is going to stop anytime soon. So all of those dimensions are continuing to grow.
Next question, the trend you mentioned in computer vision with ConvNets being revived again seems to be replicated in NLP. New tweaks to LSTMs seem to make them achieve tasks that only transformers were able to achieve before. What is fueling this development and your opinion, and do you think there will be a clear winner?
Yeah, that's a hard question. I still definitely think the transformers are better suited than LSTMs, just because of the whole. I mean, LSTMs were introduced to cope with the vanishing gradient problem, but still, I think that just having a direct access in parallel to all the tokens and doing the computation in that way seems to be, at least so far, that's what we've seen is more powerful approach. But ultimately, like RNNs are Turing complete, and all of these models are like by the universal approximation theorem can approximate any function to an arbitrary precision given enough given enough parameters. So all of these are quite potent, and maybe we'll probably be seeing convergence of various architectures, and we have been seeing, like MLP Mixer is an example. We've seen people now applying like multi-layer perceptrons, which we thought were long gone. Although there is a lot of, it's very debatable whether those are MLPs because you can treat them as COMNETs, and it gets very complicated. But like ultimately, we'll probably see some type of like hybrid approaches or merging or converging, or I don't know. Like that's some thoughts on top of my head.
Okay, fair enough. Next question on training procedures. Is there an underlying physical description of why training with mixed data is guaranteed to boost performance? Are results the same when using real automotive camera data instead of using those cat and dog data?
I'm not sure I understood the question. Maybe I can answer it offline because it sounds a bit longer to parse. Yeah.
Okay. This was raised by Alan Mahari. Please, maybe you could elaborate a little bit. The second part is really a little bit confusing. Okay. Then there's one more. Do the new approaches and techniques target only improving the accuracy, or are other goals such as uncertainty and estimation also addressed?
That's a good point, and I'll show you in a couple of slides one interesting approach where people are trying to, for example, cope with auto-distribution data. I mean, not necessarily fully Bayesian approach, but like there is some modeling of uncertainty, and yeah.
Okay, cool. And let's.
I mean, even if you take like transformers, like they are probabilistic. You have an output from which you're sampling from. It's not like when people say Bayesian, you probably mean you're estimating like distributions over the parameters, which is intractable, and so far we haven't seen Bayesian approaches scaling up, and so we probably won't see those scaling up. But yeah, that's definitely an important part, and people are working on that. It's just not mainstream, at least not fully Bayesian techniques are not that mainstream. Not that they are not promising, I'm just saying. Cool. Okay, so maybe I can start and present a couple. I have only a couple more slides, and we can open it up for questions. I love the questions. Just keep them coming. Yeah, don't be shy. Cool. Let me move from this meme onto something more serious. So theory behind scaling. We've seen the scaling, and here's some very cool research that has been going on, trying to make sense why all this works and how we can be smarter about scaling. And one of the very interesting papers that came recently from Microsoft Research is this microtransfer that introduced this maximal update parameterization method. And what it basically does, so here you can see on this chart what's going on. Instead of having this blue hexagon, which is, for example, 175 billion parameter GPT-3, you instead take a much smaller GPT-3 model, like maybe 16 million parameters or something, and by using this smart micro parameterization, however, they, I don't want to get into details, but they somehow start from this small model, and then they do the fine tuning, they do the hyperparameter tuning there, which is much more cost effective, and they basically guarantee that when scaling back up, those hyperparameters are going to remain stable even for the bigger models. And you can imagine that if you were to do that in the on the original model size, it would be super expensive. And that's what we've been seeing. And that's you simply cannot search through the combinatorial space because of the budget, if nothing else, money. So yeah, that's a rough idea of what these guys are doing, and they only have a theoretical guarantees for scaling so they can basically just theoretically guarantee for width scaling that this is going to work, but they empirically show that even scaling depth and across other dimensions, this stability criterion remains true. So as I said, let me just move this again. So we showed that in the recently discovered maximal update parameterization, many optimal HPs, which stands for hyperparameters, remain stable even as the model size changes. And by transferring pre-training HPs from a model of 13 million parameters, we outperform published numbers of BERT-large, which has 350 million parameters, with a total tuning cost equivalent to pre-training BERT-large ones. So let this sink in, because you can see that they managed to achieve better results than this big, like BERT-large. They're using a computation that's needed to pre-train BERT-large only once, and you can imagine that people who were tuning BERT-large probably took much more compute to get to the same result. And so this has quite big practical implications. This particular paper, and I can show you a small diagram just to make this a bit more visceral. You can see on the left-hand side, using standard parameterization, you can see that the learning rate, so that's just a single hyperparameter that they took to plot here. And you can see that as we're increasing the model size, and so you can see here, these darker lines are bigger models, you can see that the optimum shifts. So the learning rate will be different for all of these different model sizes. And if you were to take, for example, this learning rate here, oops, I lost my cursor. So if you were to take this learning rate, which is optimal for this particular curve, and then you were to increase the size of your model to this one, you can see that this is super very, very, very suboptimal learning rate point for this big model. Here on the other side, using this microparameterization method, they show that it remains stable. You can kind of draw a vertical line here. You can see that the minimum is roughly along that line. And you can also notice that the training loss is monotonically decreasing, whereas here on the left-hand side, probably the best model is the one with 2048 parameters. So yeah, very, very practical implications of this research. Yeah, and as I said, they have guarantees for width, and the next paper showed how to scale in depth-wise. So these guys managed to scale up transformers to up to 1,000+ layers, and we've seen such a thing in CNNs already back in 2015 with ResNets, when they actually managed to train back then more than 1,000 layers as well. And this is the first time we've seen transformers scaled up to 2,000 layers. And basically, on the x-axis, by the way, you have just the chronology, you have time, you can see the models that were published, and on the y-axis, you can see the depth, and you can see that on this particular benchmark, this model won this benchmark. So the changes that you as a practitioner need to apply to your code are super small, and you can see everything that's needed on this small snippet of code. they basically modulate. So you have here the layer norm, you have the residual pathway, you have the signal pathway. You just need to modulate the signal pathway, and they prescribe basically how this alpha should change depending on the target depth. And also they just show how you should initialize certain layers of your transformer, like FFN, fully feed-forward network, and the projection layers, etc. I don't want to get into details, but like they have another parameter here called beta, and all of this enables them to scale in depth. And you can imagine like combining all of the research I just showed you across this whole presentation, and couple that with scale, and we can just expect bigger and bigger models. Like that seems to be the case. There's nothing like that's stopping us from doing that. Okay, gonna make a quick break here.
Cool, very exciting. There's a couple of questions. What is your opinion about approaches focusing on the quality of data, like the data-centric AI proposed by Andrew?
So what's my opinion on the data-centric approach by Andrew, right?
Yeah, data-centric, I guess overall, but Andrew as an example, like.
Yeah, I mean, it's not mutually exclusive. People who are building bigger models are also thinking a lot about data and making higher quality data sets available and scaling the data sets as well. So let me just recap for those who don't know what it is, and just to verify I understand it correctly as well. So what the data-centric approach is all about is fixing the architectures, not caring that much about the architecture design per se, and instead focusing on the data. Just increasing the quality of data, I guess, increasing the number of data points, et cetera, et cetera. And then Drang is kind of very verbal and a proponent of this approach. But yeah, as I said, I think it's more of a maybe what would be the word? Just branding rather than something that's exclusively done by his group. I think many people are doing similar things, and I definitely think it's a promising approach, and I'm happy he's pushing for it.
Well, I guess if we stay with your slide from earlier about the bitter lesson, then it doesn't scale with compute. So that should probably be a big disadvantage for the whole effort of improving the data. I'm definitely a believer, especially if you want to release something for a safety critical context, and you need to look closely into your data. But yeah, it doesn't scale with compute, so might be the smaller level after all. Okay, then there's another question, which is, do you think neural learning approaches will be ultimately able to capture all of the logical symbolic rules underlying a domain, or we do need hybrid neurosymbolic AI approaches?
Is that Gary Marcus behind the question, or?
It's 𝐍𝐞𝐑𝐅𝐬 Hodai.
I'm joking. Yeah, I think, I mean, you don't have to have a strong, like, you can basically see the evidence behind this. And I think it's just the fact that if you take a look at some of the models that were super successful historically, like 𝐬𝐬, for example, AlphaZero, all of those models are neurosymbolic. You have the neural network component trying to learn the value function. You have the MCTS, am I buttering it, Monte Carlo tree search, which is more of a symbolic type of approach. And so I definitely don't see why like something like that would not work. Although given enough compute and data, I guess you can learn anything. Like that's I guess that's the premise behind people who are for pure deep learning and for like reducing the number of biases in architectures. Like it's probably feasible, but like sometimes sometimes you wanna, if you know your domain very thoroughly, then you probably know which biases are good, and then you can make it more sample efficient and cost effective to train your models if you know those biases up front. But the con side is if you make wrong decisions there, then you are definitely gonna end up with a suboptimal solution. So that's always like a peril lying in that in deciding the biases, or in Bayesian learning deciding on the priors. So all of that is very yeah, has its own trade-offs.
Okay, then let's proceed with the presentation.
Cool. I think I'm like pretty much wrapping it up here. Just briefly mentioning two more papers. One is BlockNeRF from 𝐕𝐢𝐬𝐬. Basically, they showed that they can scale NeRF, which is neural radiance field model, for those of you who are not familiar with it, to like basically whole city blocks. And they, in particular, they use San Francisco as an example. And what NeRF does is it basically can render 3D scene from a particular viewpoint. And how they manage to do that is by simply training multiple nerves, and all of these particular nerve models are trained independently, completely independently, and they care only about a certain physical geometrical neighborhood. And here you can see like briefly how it works. If you have a target view, you kind of draw a radius around the target view point, and then you find the closest nerve models that were trained, and you somehow combine all those predictions to get a final prediction. And this works like a charm. So this is definitely interesting for the autonomous driving community as a paper. So if you haven't read it, go check it out. You have the link here in the title, as I said.
So Aleksa, I have a question here. It's more of a practical question. So how do these techniques help us solve the validatable data problem? So we have this problem about having to do large scenario-based testing, right? But these scenarios, if they are, let's say they are not real and they are simulated, then how do you validate them? So in this case, does this really help us in the direction of verification and validation?
Well, I can't speak in the name of 𝐕𝐢𝐬𝐬 here, but like
in general, like, so
yeah. So basically, what I think personally is that you have 𝐕𝐬𝐬𝐬 on one side, and you have, I don't know, some other companies like Tesla, and they have completely different approaches. And I just think in general that having this plurality of research directions is a healthy thing, because ultimately nobody knows what's the correct solution here. Same goes with the scaling I was mentioning so much here. Like there is a lot of people who are kind of not happy about just stacking more layers. But I think until we see saturation, why would we stop? Like if you still have a research direction that promises something, just go ahead and explore it. Don't be smart ahead of the time. And that doesn't mean, again, that it should exclude some other research that's going on. And I just think that this parallel search is a promising thing, and that this is just one additional thing that's probably worth exploring if you want to have much more thorough 3D maps of your environment while driving. Like, that's my personal opinion.
Makes sense. Okay, thank you.
I actually think like if you use that as a synthetic environment for the simulation for your AV to drive in, or any other like simulated environment, right? In both cases, you will have the validation problem. I don't think that Gaurav, that it exists more in that kind of environment. In fact, you can even argue that it's derived from the real world and everything that makes it maybe a little bit better. But I think the problem is really just there in both cases. At least you might be able to show that any improvements that you make in these virtual worlds correlate with improvements in the real world, right? That's always the classic approach. So if you can confirm that, then you're already a couple of steps further.
Okay.
Please proceed.
Thanks for the question, Gaurav. So the final paper, virtual outlier synthesis. Here you can see that they try to address this problem of auto-distribution data. And what's namely the problem is on the left image here, you can see a moose crossing this road. And you can see that the model is fairly confident that this is a pedestrian with 89% of confidence. And you can, obviously see that that's not the case. So what pedestrian is, it's in distribution data class that the object detection model was trained on. And it's very confident, and we want to avoid this. And so what this paper does is basically proposes this method to, I won't get into the details, but you can see, like if we treat data points instead of treating images, let's focus on 2D data points. So these gray clusters, and you can see that with regular object detection pipelines, you get a map something like this. And let me help you parse this map. So what this map says is the following: if you have this very like dark, like red areas, that means that the model is confident that that's in distribution data. And when you have blue, dark blue, then that means it's OOD data, outer distribution. So if you pick a point here, the model is going to say, oh, this is outer distribution. And if you pick a point here, it's going to say, oh, this is in distribution. And just eyeballing this diagram, that probably doesn't make much sense. And the diagram on the right-hand side here makes a lot more sense, because here you can see red points are close to the clusters. And then as you go further away from the clusters where we don't have any idea of, we never had data points there, then the model says, okay, here we probably have outer distribution data in this regions of the space. So that, yeah, briefly how it's trained. Basically, they sample these virtual outliers in the feature space instead of in the image space, and by just doing that, so you have two branches here, classical branches for your object detection pipeline, just localization and classifier predicting class here. And so additionally, so somebody asked about uncertainty. So here is this is the paper I was referencing. So basically, they model the uncertainty. How certain are they that this is in distribution or out of distribution? And as you can see here, finally, the same image that we saw on the left here, now it's correctly predicted as OOD. Yeah, it would be cool to see the number behind this prediction, but at least they probably have some threshold, like 50% or something, and then this seems to be OOD. So yeah, that was pretty much it. We can stop here. This is like some shameless promotion. If you are interested in all of this, what I just talked about, if you want to stay in touch with machine learning news and stuff, I have a bunch of outlets like YouTube channel. I also open source implementations and tutorials on my GitHub. I wrote a bunch of stories. I did mention the one for getting started with machine learning. That one is probably useful for if there are beginners among you. And yeah, I'm active on Twitter, LinkedIn, and feel free to join the Discord community if you want to connect with peers, and feel free to ask questions there as well.
Okay, fantastic. There are still more questions, so I'll just go through them and read them out. One is by Sardosh again. Do you think, sorry, this is the same one, so I must be in the wrong corner. Give me a moment. Okay, I have one here. Gaurav relayed that to me from 𝐸𝐸𝐬𝐸. Will VIT take over CNN in autonomous driving industry? Visual transformers.
I don't think so. As I said, I think that convolutional prior is a very strong prior, and it has we've seen that CNNs have been there since like '89, right? Like with Jan de Koon's CNN paper. So I think it's a very strong prior. Just weight sharing is a very logical assumption about natural images. Natural images are not like synthetic, arbitrary, random images. You do have some correlation, local correlation of pixel values, and I think that CNN prior is a good one. And if we take a look at the Squint transformer, the way how they managed to make vision transformer work for dense prediction tasks such as semantic segmentation is by introducing some of those priors, which goes completely against the logic of the VATs, because the whole point was just take the arbitrary NLP transformer, do the specify layer on the input, and then you just have your quadratic computation and basically fully connected network. You're modeling your input data as a fully connected graph, not network, sorry. So yeah, I basically think that having this weight sharing and is a good prior to have. So that's my personal take on this.
Okay. Next question is from Stay Day. I have a question on nerves for AD applications. If I understood it correctly, nerves can render 3D scenes which require images from different angles, probably also from behind. How does this work in real time? Please excuse if there are misinterpretations.
I'm not sure about the real-time component. I'd have to double-check the paper. I read it a while ago, but I think somebody correct me, but I'm fairly sure it can go real-time. Like nerves have been, at least maybe not block nerve, which I mentioned, but like nerves in general, I know they can be real-time. Like there are some approaches where you don't even need a neural network. Like it's very, very fast. So I don't think anything preventing us from going real time with these models. If that was a question, if I correctly understood it.
Another part of the question was whether, like, what happens if you're not perceiving the object or your environment from an angle that would actually provide the required information, right? What happens if, like, you like individual in my environment are moving behind that observed vehicle or object? What would happen then?
Yeah, that's a very good question, and the Blocknerf paper did try to address that. So they had these visibility maps which show you how certain is the model that you can actually see something on that particular pixel. So yeah, people are trying to cope with that. That's a real problem, definitely, and yeah.
Okay, yeah, I guess in this case you wouldn't have to just interpolate anymore, but really to synthesize stuff, and of course you could be wrong. Like the okay, anyway, Puriya Sarhadi mentioned which one of the discussed techniques can be used for decision making? Are they only for computer vision, or are they tried in end-to-end driving? Is the AV problem just computer vision?
Oh, it's definitely not just computer vision. Like, perception plays a very important role, but you do need to plan, you do need to reason, and that's arguably the hardest problem, probably. Like, just planning ahead and reasoning, like basically being intelligent driver is not only about perceiving the world. And when I say perception, how I visualize that in my mental mind, like in my mental eye, is you have an image and you just abstract away some concepts, like, oh, I have a car that's at coordinate XY, and I have this object, and so you have those percepts, and then you have to make sense of those percepts. You need to understand their relationships. You need to understand like the velocity of those objects. You need to understand the context. Is this bounding box a pedestrian, or is this bounding box just like a tree? And for all of that, you do need reasoning, you do need planning, and that's a much tougher problem. So regarding the end-to-end, I think again, different companies are trying different approaches. I think some people are experimenting with end-to-end, but like I think Tesla is doing more of a neurosymbolic approach as well. Like they do have both the neural network components as well as some more symbolic approaches there. So yeah. Bunch of companies, bunch of different approaches.
Okay, then the last question from the audience. What is the value of the outlier paper? As we know, there will be always high confidence wrong detections. It was proven since 2019 in a paper at CVPR. The proof holds for any ReLU networks or carry or any activation that is piecewise linear.
Okay, that's interesting, and I'm not familiar with that research. So yeah, I wouldn't be able to give any smart reply here. Feel free to link the paper. I can skim it and maybe I'll reply to you offline.
Okay, then I do have a final question. It actually came to my mind when we started with the talk, and somebody raised the question of starting with machine learning, getting familiar with stuff. What I've observed over the last year is that machine learning became way more professional, pretty much industrialized even. So the question would be, how accessible is the domain meanwhile for individual researchers, people just getting started, where like large companies are building huge networks that completely outperform anything that, you know, an individual person could easily come up with? What's your opinion on that?
It's a good question. Well, if your goal as a researcher is to play the scaling game, then yeah, you probably you'll have a hard time unless you join some industrial lab or a company. Then again, those companies usually publish those models and checkpoints, and so the so-called is it foundation or foundational models? Again, branding. But like, in any case, you do have those checkpoints, and you can save a lot of money. So somebody like spent millions of dollars to train that model, and now you have it available. You can just fine tune it. And so I don't think, if you are just getting started with the field, I don't think you should be scared, because there is people that have so much resources. I think there is a lot of research going on where you don't even need that much compute. Like some of these theoretical papers I mentioned, you probably don't need as much compute. It depends on what you're trying to accomplish. But if you're trying to play the scale game, then joining some of the biggest AI labs or companies is probably a good thing to do. But I don't think that's necessarily the most impactful research in the long run. Who knows? Yeah, I'm optimistic about this.
Quick follow-up question: what would you to which direction would you guide aspiring researchers? What is an impactful topic to focus on if you don't want to join the scaling game?
I'm a very, so by the way, I'm not a researcher officially, but like I'm very curious in all of this, and I spend a lot of time reading papers. My personal take on this, and that's something I'm doing, is very, very lateral and very broad. So I'm currently even learning about genetics, neuroscience, developmental part of human life, and how brain is basically how do we start with a zygote, which is like you have a single cell, and then all of a sudden you end up with a fully blown human brain, and we usually just start from the adult brain, and we just ignore the whole procedure that generated the brain. So you can imagine one of the models of that embryonic development could be some cellular or like automata type of a process where you're building up this brain which is super symmetric. And yeah, what I want to say with all of that is that maybe try and not be that mainstream. There is many opportunities out there. I think the best thing to do is maybe fuse multiple areas of research. Like I don't see many people working in the intersections of, let's say, neuroscience and ML or genetics and ML, or even, like as I said, this embryonic development or early child development where you're trying to understand the cognitive capabilities of children, all of that. I think there is a lot of space for people to be domain experts in some of those, and then learn machine learning and deep learning additionally and merge those two together. I think there is a lot of opportunities especially for science and understanding intelligence, like in general. I think that's a promising direction.
Okay, thank you very much for the presentation. I enjoyed it a lot. Thanks for preparing everything. Also, I know it was you said it only took you 45 minutes or something like this, but I guess there's all of the work that you put in the videos and everything before that made it possible. So again, highly appreciate that you joined us today, and thank you. And with
thanks for the invitation, and I really appreciate it.
Awesome.
Thank you, Aleksa.
Thanks. And with that, Gaurav, please take over.
Yeah. So next up is Matthieu Worm. He does not need an introduction to the AD community because he's been a simulation and test solutions expert at Siemens Digital. Before that, he was at Moog and Toyota, and he's been he's co-founded within Siemens the Simulatic environment, and now he is more focusing on simulation and digital twin aspects, mostly from the Belgium region. So Matthieu, great to have you here, and yeah, looking forward to your presentation.
Cool, thanks. I had one more question to Aleksa, maybe to start with, and it was related to the earlier question about whether autonomous driving is all about computer vision. Do you see papers, publications on other media than image data, like radar data, like other data that autonomous vehicles typically take in to do their perception tasks?
That's a good question. I mean, I've seen some maybe like point cloud papers,
Yeah.
but not that much. Maybe like what was the name of the model? PointNet. But that's a very old approach. Yeah. To be honest, I haven't seen. I think that's a lot of companies are doing proprietary stuff, and then it's probably harder to find papers like working on radio or stuff like that. And yeah, it's usually just images, I guess.
Yeah, 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 exactly. And I believe that in the autonomous vehicle space, this multi-sensor approach is definitely kind of the norm. So I would will be interested to see how that develops further. Thanks for having the opportunity. The original speaker from 𝐸𝐲𝐻 was planning to talk about the ADAS autonomous vehicle toolchain. I think I can address that topic, taking more of a Siemens perspective, obviously. What I believe is important to start from is the actual end user. And when we discuss autonomous vehicles, it is about, in the end, about people that actually are willing to step into these cars. And in order to do so, there's high expectations in terms of safety, efficiency, comfort, ease of use. And in the end, the funny thing is that the competitive discriminator will definitely not be safety, as we just assume safety to be equally important for every vehicle that is on the road. Kind of similar to the aerospace industry, where you consider the airplane to be safe, even though there are still a lot of accidents ongoing in the world today. So safety is a prerequisite. The key drivers for adoption and for acceptance of self-driving vehicles, I think, are in domains of efficiency and comfort. We will only adopt and start using self-driving vehicles if we feel that it gets us from A to B faster, cheaper, at least as comfortable as we are used to it, to having our own car today. So there's a lot of stuff to be worked on, and somehow we, and when I say we, I mean the automotive industry, is required to translate that into products and into vehicles that have a proven performance. We did a podcast with Mark Rosekind from 𝐍𝐞𝐈, and he says that in aviation they do not compete on safety. We deliver safety as an industry, and there is a very large certification industry around. And I hear some beeps for chats, but I cannot see them right now. Maybe we address them. Let me know if there's questions.
I also don't. I'm also hearing some beeps, but I don't see any chat. So
okay,
it's probably just some feedback. So
yeah, please let me know if there is a question.
I will.
The funny thing is that right now, compared to the aviation industry, in the automotive world of today, safety is a major sales argument. Volvo's reason of existence is safety. So we will need to prove safety in the autonomous vehicle space, and the expectation is that there will be more analogies with the certification processes known from aviation, and that will trickle down into the automotive industry. However, a major difference is then that you can certify an aircraft once, and then you get it in the air and keep it flying for years or even decades, whereas an autonomous vehicle will be a continuous learning system. So what we need is a verification process that allows for continuous improvements, taking in data in this loop, capturing data, monitoring behavior, doing an analysis and a diagnosis on the data that you capture, learn from experience, ensure that you redesign, further improve the performance of your system, and then run validation and verification loops, allowing you to, through over-the-air updates, improve the performance of the vehicles. So if you assume such a process, you see the need, the massive need for data. I believe not only camera data, there will be more data modalities that need to be integrated in such a loop. And the toolchain and development process that we support from Siemens side maps on this proposition. And that's pretty unique in the sense that there is no competitor that puts so much focus on the combination of recorded data and synthetic data. So we, through a partnership with B+, we have now integrated the data recording solution to have these ruggedized compute systems that you can mount in the back of a vehicle, collecting terabytes of sensor data. As said, it's not about radar data only. There is a lot of it's not about camera data only. There's a lot of LiDAR data, radar data to be captured, potentially also ultrasonic data and other means of data. And you need to synchronize that with the vehicle data itself, the information that comes out of the CAN bus of the vehicle, and combine that all and not only record it, but also be able to get it into a cloud and then make it accessible to engineers for training. I like very much there was a question on the overload of data. We actually have too much data rather than a shortage of data. The part of the solution of these recorder systems is the capability to process that data and to select actually the kind of data that you are interested in. So we can actively search for specific scenarios in real life and make the car record those scenarios. And in the example that's on the screen right now, we look for pedestrians. There is a pedestrian recognized that triggers then the recording, but it does not only take the recording as of the trigger. It buffers information, so you collect data 20 seconds before that person arrives, up to a couple of seconds after that person arrives. But you can do kind of targeted search and upload then the relevant data even from the vehicle directly into the cloud, rather than that you need to wait for the vehicle to come back and pick up the recorders and load the data then. If we have a base set of interesting scenarios, the value of synthetic data comes into play. So we need to extend recorded data, known unsafe scenarios with unknown unsafe scenarios. And we can do that by generating a scenario description and start to parameterize that description and generate new variations of these scenario definitions. We use OpenDrive, Open Scenario formats for that, and we work with a startup called 𝐸𝐵𝐺 that has developed a very rich set of safety metrics that go way beyond the traditional safety metrics, like time to collision, for example. So in these scenario descriptions, we identify basic scenario elements. We cut the scenario description into these scenario elements and then start to generate new variations with distributions over the parameters that we have identified, enlarging very quickly the set of scenarios that we can use either for training or for verification purposes. And we do that with different sampling techniques. And so if you look at the pictures on the right, if you would do 2,500 runs, you can quite accurately determine the corner cases. So the cases that are on the edge of an actual collision or a non-collision. So you can an interpretation for the pictures here is that you have a vehicle A speed and a vehicle B speed on the X and the Y axis, and that depending on their relative speeds and the environmental conditions, there will be collisions. You're interested not so much in the obvious collision scenarios. You're not interested in the safe domain scenarios, but these edge cases, that's what we are interested in. And it's somehow it touches on the outlier information that we've just seen. If you want to do this more efficiently with sampling techniques, we can do Hypercube sampling within our toolset. So that's an automatic switch, where we can get a pretty good estimation of where these corner cases are. But if we use smarter adaptive sampling techniques, we can even go more into detail and mimic with only 10% of the simulation runs pretty accurately where the domains of interest are in the verification of these cars. I would then move to the design and explore phase, but I saw there was a pop-up of a question. Is that something that we should address now?
We can definitely. So there are two questions. One is, let's take the most recent one first. What are the superiorities of a digital twin to an ideal hardware in loop or a device driver in loop?
Sorry, can you repeat it?
In your opinion, what are
Yeah.
the superiorities? So what is
Yeah.
what is the advantage of digital twin as compared to an ideal hardware in loop or a driver in loop simulation?
So it's definitely in the combination. Eh? So I don't believe in a digital twin only approach. It's in the combination of recorded data and simulation. And the superiority is definitely in the fact of controllability. Yeah? So being able to use sampling techniques to extend your scenario base, to actively search for the scenarios that make the controller fail, and be able to prove the performance over a much larger scope of conditions than you can possibly do in a real environment. I think that's the key driver in the use case of autonomous vehicles. I can talk a lot more about the value of digital twins in other industries.
That is definitely one of the factors. Yeah. There's another question about the safety force field formalism. So the question is that safety force field formalism that you were using in those plots, the plots that we were seeing on the previous slide, probably? So is that technique? Yeah. Yes. So I think the question is, are these safety force field formalisms, or how are these plots called? The ones on the right.
I don't know. I'm not familiar with the terminology.
Okay.
Happy to get back to that.
Mm-hmm. Yeah, I think we can go on. Yeah.
So if you're able to capture scenario data and enrich that scenario database with synthetic data, we can start to generate scenarios and test sensor system, perception systems, control systems in virtual environments in a massive variety of conditions. And what then and related to also my first question at the beginning of the presentation to Aleksa is here the need for physics-based information becomes really important. So having just flat images will not give you the sensor inputs that you need for a proper verification of the performance of the perception system. And to illustrate that a bit further, we see here a Tesla dashcam recording. And at this point in time, the autopilot starts beeping and applying the brakes, even though the car in front did not yet brake. So there's no deceleration yet of the car in front. Still, the Tesla is able to predict an accident, an upcoming accident, and it does that based on radar data. So there's camera data that will have huge difficulties predicting this, but the radar data is able to, as you have radar signals that bounce on the road and the bottom of cars, that bounce on the guardrails of the vehicle. So if we rebuild this in simulation, in a physics-based simulation environment, we mount these sensors virtually on the car, and we then reproduce the raw radar signal. We will see that you see here the raw radar signal coming out of the virtual engine. We see a reflection of the blue car, which is the car in front of the red car. So due to multi-bounce effects of these radar signals, we can see a deceleration of the blue car, and that deceleration of the blue car is then the actual input for the autopilot to apply the brakes. So if you want to design but also verify systems like these with multi-sensor modalities and inputs, then physics-based sensors are a critical element.
So Matthieu, probably now is the right time to bring up a question. So I was waiting for the right time to bring a question from Bob. So I'll read out the question. So he's saying that I'm always confused by this continuous learning approach. If you have a car that is driving itself and works, why do you need this complicated data lifecycle? It makes only sense to have the complexity if the product is unfinished, as in case of in his words, Tesla FSD.
Yeah.
But if the product is functional, then the need of frequent updates is reduced, isn't it? So it's, that's the question.
Yeah. And then, so I think the answer is in the definition. Can you be perfect, right? And is it possible to design the perfect system for an infinite variety of conditions? And I'm convinced that that's not the case. So it, and obviously Philipp Koopman is here the authority explaining to the world how important it is to have a very thorough, safety-driven development process. But in the end, I think we will not get to a situation where there is manufacturers and also customers, by the way, that are willing to wait for autonomous vehicles that will have zero accidents. So there will be a transition phase, and it's in that phase that learning is massively critical. And over time, I would still expect that there will always be new situations that were not taken into account when designing a self-driving car. And it's easy to have a human driver in the loop that will take care of a large number of unexpected situations. And secondly, that by being human, that we also accept that people make mistakes and that accidents happen. It is much more difficult to accept accidents from a machine to happen.
I agree. And how I usually answer this is that there's also this long tail of unknown unsafe, right? So this is one way that you continue to reduce the space of unknown unsafe scenarios.
Yeah.
And that's why it needs to continue in a simulation environment as long as it takes, because this tail is really long.
Yeah, and to be honest, I think Tesla is pretty quick with releasing software
with
without
adapting.
being with it. Yeah.
Go ahead.
Cool. So then we enter the validation verification stage, where what you need and what is currently not state of the art in the automotive industry is a kind of continuity throughout your verification pipeline. And if you, for an adaptive cruise control system as we know it, there is roughly 140 tests executed on a proving ground. And if you have completed all those tests, you can allow the vehicle to go on the road. For the massive number of scenarios that you want to test in a fully autonomous vehicle, you need to rely on a lot of virtual results, as we just discussed. What is then needed is that you bring continuity in your verification pipeline and ensure that the critical cases you identify in a model in the loop or software in the loop, massive simulation run, can be repeated in a hardware in the loop, driver in the loop, vehicle in the loop, real-time test setup. And I remember the picture that Aleksa showed on, it was maximal update parameterization, if I wrote it down correctly, ensuring that you capture a complex, very detailed analysis. And in this case, that could be if you use a very detailed vehicle dynamics model in a model in the loop test series of test runs, you won't be able to run that model in real time. So you need to do a kind of model order reduction to offer that model to the people that do real-time testing. But you want to ensure that that model in the hardware in the loop setup is representative for the results that you had in your model in the loop testing. And likewise, if you then move to proving ground testing, you want to be able to put a driving robot in that vehicle and have the exact same braking timings and steering inputs as you had in your virtual environments, to ensure that you can actually compare and also build up the trustworthiness of your virtual results. And if we then tie that back to that starting point of certification and more aerospace kind of procedures for certification, then I strongly believe that there, and your NCAP is on that path in its new test protocols, that the combination of a large number of virtual results needs to be accompanied with actual test results, and you need to prove that there is that these are comparable. So that's something that that we work on strongly in Siemens. As I started off, we have pretty unique proposition in terms of combining actual testing capabilities with the virtual world, recorded data and actual data, but also simulation and test. So there is the capability in PreScan 360 to generate these scenario variants and to automatically run those variants, and then also to couple those to the safety metrics of 𝐼EX. So these the 30 or 40 different safety metrics that they can check on these 100,000 runs in a cloud environment and give you back the domains of interest where the controller fails, can even come back with suggestions on how to improve your controller behavior based on the tests that you've done. But then we need to be able to redo some of these tests in a driving simulator setup with real-time models, with proper vehicle dynamics models and powertrain models that you have an accurate prediction of braking distances. And then lastly, get to a proving ground and be able to, using these kind of driving robots, be able to very accurately reproduce the behavior of that vehicle. That's the whole, that's an integral part of the tool chain and development process as we believe in at Siemens. So closing off with a kind of summary, and then again open for more questions. What is really critical is that we are able to move away from the traditional, and we're talking traditional automotive industry, the majority of the automotive industry, that we move away from the traditional validation verification standards and way of working in the ADAS context, where you always have the driver to fall back on, and move towards a massive reduction in the number of different tools being used by the different departments, ensuring that more people get access to simulation data and that data can be exchanged, but also reduce the dependency on recorded data. The vast majority of the verification work today is still done with recorded camera radar data. The dependency on that can be reduced with proper physics-based simulation tools, which will allow that continuous integration deployment loop with traceable information connected into your PLM environments and your all the environments that are so much needed to document a certification process as it is known in the aerospace industry. And lastly, we need to ensure that people are not simulation only or test only, right? It is in the combination of recorded data and synthetic data, and it's in the combination of simulation and test, and bring that together in a seamless verification process. That was my last slide.
Mm-hmm.
So happy to answer further questions if there are.
Thank you very much, Matthieu. This is very, very insightful, and a few new things that I learned. Will be Googling them afterwards, especially those plots. I need to find out what those plots are called.
Okay, yeah.
There's a question from Dennis. He's asking two things, and because these are really two big paragraphs, so let me try and summarize what he asked.
Okay.
Right. So in the latest question, he's asking about simulation for machine learning algorithms. So basically, using simulation to train machine learning or deep learning algorithms. In such a scenario, how can we be sure about what fidelity of the scenario is good enough?
Yeah.
So I think that's the essence of the question.
Yeah.
So
and honestly,
the example he has used is of fog or a scene with fog or rain. So how do you decide when to stop in terms of fidelity? which we have on the screen as well, right? So
yeah, and my honest answer is that I don't have the answer. So it's definitely a domain of a lot of research, and how to quantify uncertainty and how to do a validation of the work that's being done. And there's a lot of small cases where we also do these validation runs. So for very individual, very controlled conditioned cases, we do run these validations. We also give a kind of validation report with the synthetic models. And so if you use the physics-based models that are available in these tools, you get a kind of validation report for the specific sensor that you use. Still, there is uncertainty, and for me, that's also part of the element why it is so important to combine recorded data with synthetic data.
So probably a follow-on question on this from my side. So I don't know if you have followed the projects that came out of the Pegasus project, the VBM and set level 5 projects. Is then, for example, operational design domain and the standardization going in that direction a way to help us with the fidelity
Definitely
in simulation world?
Yeah, and so the uncertainty in blue sky conditions is much lower, obviously, than under tough weather conditions. So if we have accurate and simple ODD descriptions, then it will also be easier to put a number on the uncertainty values for sure. Yeah.
All right. Felix, do you have any question?
I do. You had your radar when you were talking about the radar simulation before, and you were arguing that it has to be physically accurate, otherwise the simulation is worthless. Or not very useful. It reminded me of like Aleksa presenting this nerve approach, and I think it was already brought up there by Gaurav, like how could this be validated and everything. And I didn't think much about it before, but now that I think about it, well, like how valid can that kind of data be? On the one hand, you could argue that it was collected in a physically accurate way, right? Because you collected it with a camera, and there have been like a bunch of effects striking there. But on the other hand, like the deep neural network has also like combined many of these camera images, like the lighting may not be accurate anymore. It may be distorted somehow. Also, it's possible that things are warped to some degree, at least.
Yeah.
I'm just thinking about this, and I'm wondering, like you have much more experience with that. What's your take on it?
Yeah, no, that was also for me the reason to ask, what about other sensor modalities? For us, these 3D environments contain a lot of material data, right? So and if we look at trees or people and clothing and all the like very important objects for autonomous vehicles to recognize, then not having these kind of reflective properties being part of your environmental model, makes it very hard to come up with raw sensor inputs. So for me, the reading of Waymo's approach and building these scenes, I have difficulties believing that they train or develop their perception systems with that. I can definitely imagine that it's worth a lot for demonstration purposes and for showing off, look what we are capable of. But to develop and particularly to verify the performance of a self-driving vehicle based on these block nerve environments, I would be surprised. I do not know of the paper that describes that. I typically see other approaches also of Waymo in the virtual world.
I think it might be more helpful for planning and control.
Yeah.
So more downstream tasks where perception is not required, or it's already
could be.
solved.
But and then you can question if you cannot use much more simplistic models to train that.
Felix, go ahead.
Yeah, yeah. I think for now it's just a byproduct, and you could use it for something like Street View, similar applications. So I wouldn't say that it's completely off or useless, but still, I like it. It immediately raises the question whether it could be used for AV validation. You mentioned now that you don't have any material properties in there for any other sensor modality. That's true, but if you have like removed the effort for all of the 3D models and textures, if you can get that for free, and you just have to add material properties, then that's already a pretty big win. Probably that's probably the biggest amount of work, to be honest, that you've already saved.
And by the way, one of the key Street View companies make use of the software also to capture, to design their vehicles, and they actually want to capture material properties based on different sensor modalities that they will mount on these vehicles. So we definitely will see more 3D accurate world information also coming available.
I'm also wondering if you can, to which degree you can infer material properties. That should be something that you could also learn. But I guess that's...
So at least I worked on a project probably in 2016 or 17 using LiDARs to identify the properties of the road. So to basically understand, and yes, it is possible, and also computer vision. So both on camera based and LiDAR based, it should be possible. I think there's enough body of research on that as well. But nothing that I've seen being implemented on in scenario-based testing area. It's more still in research, I think.
Yeah. No, and there is this road. So the 𝐶enomatics LiDAR company, they have developed now a road scanning LiDAR application. So I can imagine that as part of their object, that they can recognize a tire not only based on the shape, but also the kind of signal that they get back. But I don't know.
There's 2 more questions in the Q&A section, Gaurav.
Yeah, I see them. So actually, the second last question, I see that's very okay. I'll still go ahead and ask. So the question is, any thoughts on how the Siemens approach could also leverage over-the-air updates? Also, we hear a lot about the term software-defined vehicle. Any thoughts on this? It's very broad.
Yeah, it's so broad. So I can only say that it's a very important trend for us, and that especially the colleagues from former Mentor Graphics, now Siemens EDA, they work a lot on these topics and also the electronics that are needed for that. We put a lot of work in 5G topics and testing and verification, which is way beyond my scope. I can only acknowledge that it's really important and that it will also play a role in our portfolio.
Yeah, and probably the last question for today, then we can close the session. So how do you see the role of independent validation entities like, like the organizations like TÜV? Should they have access to the simulation environment and data? So I would take the liberty to extend this question and say, how should homologation authorities like TÜV in Germany, or maybe CITRAN in Singapore and the others in China, what data should they use to homologate and to give Fit for Road certificate for ADAS and AD software?
You mentioned Simulytic, the startup that I was, or the startup is a big word, the Siemens venture that I was part of. There we approached the insurance industry and saying, look, how are you going to insure a fleet of 1,000 robotaxis in a specific city without having historic data? And there is the immediate tendency of the insurance industry is to say, look, if you can give me a virtual environment that mimics the real environment, then I will put pressure on the Waymos and the Motionals to give me access to their controllers, to couple that to your virtual environment, and with that get a smart, get a good rate on their insurance premiums. And if they are not willing to share insight into the performance of their vehicles in that specific ODD and that specific geographical area, then I cannot give them the offer that I can otherwise do. So I in the end believe, and for me the analogy with aerospace is important. I think that in the end, if it's really these 10 to 15 players worldwide that are able to develop level 4, level 5 self-driving technology, that it's such a small number of players that regulation will, that it will become pretty pragmatic to apply a regulation and to set standards for that. And I think as a society, we also want that and would benefit from that. So this is a massive transition, and it will be very tough to convince all the individual OEMs that believe that they are the next player in the AV space to individually go and standardize on these harmonization processes. But in the end, my expectation is that it's these 10, 15 players that now have the budget and scale to develop true self-driving vehicles, that they will be the ones that need to go through certification.
That's a good point. And I think you also raised insurance companies as a party to this decision.
Yeah, they will be first.
Yeah.
Before the regulation comes, the insurers need to play their game. Yeah.
They might be. One might say that they might be also the business drivers and the stakeholders who would actually go ahead and define the way it should be done. Yeah.
That's why Simulytic will be a successful
fascinating
venture.
Yeah. Fascinating. Thank you very much, Matthieu. This learned a lot today, both from your presentation as well as Aleksa's presentation. And special thanks to you also for jumping in the last minute.
Cool.
And yeah, over to Felix.
Yes, thanks to you, and thanks to everyone for joining. Again, this will probably be the last virtual session, at least for some time. We want to resume with physical sessions, and I hope that we'll meet in one of these funny and exciting physical sessions that we had before. In spring and summer now, we'll organize some.
Excellent.
Thank you, everyone. Then have a good evening. And yeah, see you physically sometime soon.
Cool.
Bye, Matthieu.
Bye.
Have a
Thanks.
good evening.